Dear all students, in these topics, we don't just want to talk about the mechanical waves. So this can be the list of the topics that we need to cover. The first one is the types of the wave that we just want to study. And then later on, we just mainly talking about the wave on a string or the cable, okay, or on the rope. So we need to learn about the wave function of the wave on the string. And we need to learn about the superpositions or the summation of the two traveling waves. And then finally, we talk about the standing wave on a string. Then later on, we talk about the sound wave. Okay, so the idea just be the same as the wave on the string. We talk about the standing wave in an organ pipe. We talk about the sound intensity, and then finally, we talk about the Doppler effects here. Now for the types of the waves. If we just want to categorize the wave due to the medium for the propagation, so we can categorize into the two types. The first one is called the mechanical wave, and the second one is called the electromagnetic wave. The mechanical wave requires the medium for the propagation of the wave. For example, the sound wave, right? The sound wave just require the air, okay, as the medium for the wave to travel through the air. Otherwise, we cannot hear the other people speaking. And for example, we can have the water, right, which is the liquid, and we can have the wall, which is the solid, as the medium for the propagation as well. The wave on the string, so as it's called, right, we just require the string for the wave to propagate on. The water wave, okay, require the water as the medium, and then the wave on a spring, so just require the spring for the propagation of the wave. So these types of the waves are called the mechanical wave. So it's the main one that we just want to study, the same as the names of this chapter. And then we have another type of the wave. It's called the electromagnetic wave. So as you can see the name, right, it just comes from the electric field and the magnetic field. Okay, so we're gonna learn about this one in the general physics too. So now for the electromagnetic wave, right, for example, we have the visible light, okay, we have the radio wave, the infrared, and etc. Okay, so these types of the wave doesn't need the medium for the propagation. For example, we can see the light from the sun, and we know that between the sun and the earth, right, it's just the empty space, so there's no medium between the sun and the earth, but we can still see the sun, we can still see the visible light. Okay, so it means that this type of the wave doesn't require the medium for the propagations. But now, if we just want to categorize the wave by the direction of the oscillations, so then we can categorize into the two types. We have the transverse wave, and then we have the longitudinal wave. For the transverse wave, it means that the oscillations of the wave are perpendicular to the path of the propagation. For example, from this picture, if the wave is traveling to the right hand side, and then if the medium of, let's say, the string wave, okay, and then if the medium of the string wave is just propagating up and down in this path, so this is called the transverse wave. Okay, example of the transverse wave is the wave on the string and the electromagnetic wave. Another type of the wave is called the longitudinal wave. Okay, it means that the oscillations of the wave are parallel to the path of the propagations. For example, if the wave is propagating to the right hand side, but now the molecules of the medium of the wave, right, it's just oscillating parallel to the propagation, so this is called the longitudinal wave. For example, the sound wave. Okay, so let's check out this website. Okay, so let's check out this website. So you can find the good simulations on this one. Okay, for example, let's consider this picture. So this one is the transverse wave. So you can see that the wave just propagating to the right hand side, right? But then the molecules of the wave, right, just oscillating up and down, which is perpendicular to the direction of the propagation. So this type of wave is just called the transverse wave. And the other type is called the longitudinal wave, right? For example, if we follow the red dot here, okay? So the red dot, right, it's just oscillating to the left, to the right, to the left, and then to the right. And then compare to the direction of the propagation of the wave, which is just moving to the right hand side. Okay, means that the oscillations of the wave, right, or the oscillation of the molecules just parallel to the direction of the propagation of the wave. So that's called the longitudinal wave. Okay, so now we just want to move on to the next topics, right? So it's called the wave on a string. Okay, so it means that, I mean, right now we just mainly consider the transverse wave. Okay, we just mainly consider the transverse wave because the wave on a string is just a type of the transverse wave here. Okay, so let's talk about the wave function first. What is the wave function? The wave function, as it's called, right, it's going to be the function that we can use to describe the characteristics of the wave. Okay, for example, if we have a wave as the pulse wave, the pulse wave just look like something like this, or we can have the triangle wave, or we can have the rectangle wave. Okay, so if we just want to describe, I mean, the property or the characteristics of this type of wave, right, we need to find the wave function for that type of the wave. Then we can just write out the forms of the wave function to be something like this. Okay, so the y here is going to be the displacement along the y-axis. Okay, because, I mean, right now we're just talking about the vertical oscillation, right, compared to the direction of the propagation. So it means that the wave here, it just oscillate in this direction on the y-axis here. But now the x is going to be the position on the x-axis. It means that it's going to be the position that the wave will travel to. Okay, so in this case, the wave is propagating to the positive x-axis. Okay, so that's why we have the x-axis here. And now for the t, it's going to be the time of the the time travel, right? Then the v here, okay, the v is going to be the speed of the traveling. Okay, so it's going to be the speed of, I mean, the traveling of the wave. So for the propagating wave, okay, for the propagating wave, the wave function must have the argument to be the x plus minus the v times the t. So I'm going to talk about this side later. Okay, but the thing is, the wave function, right, must have the arguments to be the x plus minus the v times the t. For example, you can have the function of the wave to be something like the y xt, right, equal to, I don't know, maybe just 3 times the e to the negative, maybe negative the x plus minus vt and then square. Okay, so you can see that we have this function, right, and then the argument of the function, right, it just depends on the x plus minus vt. So it means that this wave function, right, is going to be for the propagating wave. Okay, so in this class, we just want to talk about the two types of the wave on the string. So we have the pulse wave, okay, and we're gonna have the sinusoidal wave here. So we mainly talking about the sinusoidal wave, but then first of all, let me just talk about the pulse wave first. The pulse wave is just something like that you try to disturb, okay, the string, just one punch, okay, and then you're gonna have, I mean, this type of the pulse. traveling on the wave. For example, if we check out this this one. Okay, so this can be example of the pulse wave. For example, if we consider this picture. Okay, so we have the pulse wave traveling to, from the left to the right, and then go to this moduli, and then some of them will be transmitted to the right hand side, and some of them will be reflected to the left hand side. Or we can have this one, right? The pulse wave just hits the wall and then rebounds back. Okay, so this is called the pulse wave. And then we can have another type of the wave. It's called the sinusoidal wave. So as its name, right, sinusoidal just means sine function or the cosine function. So it means that this type of the wave, right, is going to depend on the sine function and the cosine function here. Okay, so this is going to be one of the general forms of the wave function. So you can see that we have the sine function, right, and the y here is going to be the displacement along the y-axis. Okay, and then this sine function, we have the argument to be the depending on the x plus minus the v times the t, as I just mentioned here before. Okay, so that's called the sinusoidal wave function. Then if we make the plot between the y, x, and then the t, right? If we make the plot between the y, x, and then the t, okay? So let's consider the first picture. Okay, so let's consider the first picture here. If we take the snapshot at a specific time, okay, so let's say that this will be the snapshot at a specific time t. Okay, so it's be the snapshot at a specific time t. Then you can see that, okay, the wave will just look something like this, right? Just look at the sine or the cosine functions. So let's talk about the some property of the wave first. At this position, okay, it's called the crest of the wave. The crest just means the top of the wave. Okay, and then also this is going to call the crest of the wave as well, right? And then at this position, okay, at this position, okay, it's called the trough of the wave. The crest means top, right, and the trough just means bottom. Okay, it's just called the trough of the wave or the bottom of the wave here. Okay, and then the maximum displacement along the y-axis here, we use the symbol as the capital A. Okay, so this capital A, right? So this capital A is just called the amplitude of the wave. Just called the amplitude of the wave, which is mean the maximum displacement would say the maximum vertical displacement of the wave. Okay, now the lambda, right? Okay, if we look here, if we just follow this path, right, it's just coming from here and then go back to its original position, right? So now this lambda, it just called the wavelength. Okay, it just called the wavelength of the wave. So from this to this, it's called lambda. Actually, it should just move this down a little bit. Okay, so now this lambda is called the wavelength of the wave. If we have unit as the meter, so the same as the amplitude, right, is going to have unit as the meter as well, because it is the displacement, right? And the lambda just be the length of the wave. Okay, so as it's called, right, it's gonna be the length of the one wave. Okay, so we talk about the x, v, and the t already here, right? So then finally for the phi, okay, what is the phi? The phi here is going to be the initial phase. Initial phase of the wave. Okay, it's going to have the unit as the radian or the degree. So that's the unit of the phi, the initial phase. So now for the initial phase, right, it's going to depend on the initial condition. So it just depends on the initial condition. So it means that the question just have to give us the initial condition. So then we can just find the initial phase here using these equations. Okay, and that's it. Okay, so let me just move this to this one more time. Okay, so then from the picture, right, so we can get that this is going to be the amplitude, right, of the wave. So it's be the maximum what we call displacement of the wave, and the distance from the crest to the crest, it's called the wavelength, the lambda here. Also, now if we look at another type of the pictures, right, another type of the graph. Okay, but now, okay, we have the y-axis, right, as the same as the previous one, but now for the horizontal axis, right, it's with the times t. So in this case, it means that if we follow the path, okay, if we follow an oscillation of the particle on the wave, okay, if we follow an oscillation of the particle on the wave. So let's look here. Yep, this one. Okay, from this website. Okay, so you can see that the wave, right, we're just traveling to the right hand side. But then if we follow the oscillation of an particle on the wave, right, you can see that the particle just oscillating up and down, okay, up and down here. So that's why we can just make the plot between the y and the t just look like this. Okay, so it means that in this case the particle will just moving up and down, up and down, up and down, and etc. So then the same thing, we can define the amplitude, right, of the oscillation to be something like this. So this will be the capital A. Oops, sorry. Actually, I should just highlight here, and also I should write down as we just follow an oscillation, okay, of a position x, okay, on the wave. Yeah, we just want to make it clear. Okay, so then again, but now we can define the distance between the crest to the crest, okay, and the crest to the crest, in this case, to be equal to the capital T. So what does this mean, right? The capital T here is going to mean the period, okay, the period of the oscillation. But then what is the period of the oscillation, right? The period of oscillation is going to be the time, okay, the time for one revolution. Okay, it's going to be the time for one revolution, or it's going to be the time for one oscillation. It will have the same meaning, but let me just say it. Okay, the time for one oscillation. Okay, so it means that okay, if we just time the motion, the movement of this particle, right? So you can see that okay, the particle just go up and then go down to its original position. So how much time is that, right? So that's called the period. Then again, right, it's gonna have the unit as the second. Okay, it's gonna have the unit as the second as usual. So you have learned from the previous chapter, right, that we have the relationship between the period and the frequency. So then we can get that the frequency, okay, the frequency of the oscillations, right, the frequency of the oscillation here. So let's say the F, okay, is going to be equal to the 1 and then over the period T. Oops. Okay, it's just equal to the F, equal to the 1 and then over the period T. It's going to have unit as the Hertz or the H and C as usual. Okay. Okay, but now let's consider this equation again. So I just want to do something. So let me just make the copy. Okay, just come to this equation again. Now, wait, actually it should talk about the speed of the wave first, sorry. So the speed of the propagation of the wave, okay. Okay, so now let's consider that if the wave is traveling with the constant speed, right? If the wave is traveling with the constant speed here, so you can see that okay, the distance between the crest to the crest, right, equal to the one wavelength. And let's notice this: if the wave, right, travel with the distance equal to the one wavelength, you can see that this particle will just oscillate, right, up and down with the times equal to the one period. Okay, so in this case it means that we know that the speed of the propagation, right, the v equal to the distance over the time. So in this case is the distance equal to the one wavelength. So it means that the time for the traveling is equal to the one period t, or we just can say that it's just equal to the f and then times the lambda. So this is equation of the speed of the propagation of the wave. It's gonna have unit as the meter per second, because lambda is meter, right, the time is second as usual. Okay, so now let's come back to these equations. Okay, so now I just want to multiply the 2 pi over lambda into these two terms, and then here, right, it's equal to the a and then times the sine of the, okay, we have the 2 pi x and then over the lambda plus minus 2 pi times the v and then over the lambda times the t, right, and then finally plus the phi. Okay, so now I just want to define two things. Okay, as highlighted here, I just want to define two things. Okay, so let's define. Okay, let's define the wave vector. It's called the wave vector. Okay, let's define the wave vector of the wave. The symbol is the k. Okay, is equal to the 2 pi and then over the lambda. So you can see that it's gonna have the unit, right, as the radian per second, because the 2 pi we have unit as the radian and lambda. Lambda is meter, so unit is radian per meter. This is the definition of the k, the wave vector. Okay, and then look here. Okay, so then we have the 2 pi over the lambda, right, and then times the v. Okay, so in this case it's gonna be equal to 2 pi and then, okay, the v over the lambda equal to what? V over the lambda equal to the frequency f, right, equal to the frequency f, or then just equal to the 2 pi and then over the period. Okay, so then in this case we can define the angular frequency. Okay, so it's just quite the same as, the simple motion, right, that we have learned already. So the angular frequency, we use the symbol as the omega equal to the 2 pi times the frequency and then equal to the 2 pi and then over the period t. So this is called the angular frequency. It's gonna have unit as the radian per second. Okay, as usual, the radian per second, because the 2 pi is radian and the term is second, right? So radian per second. Then also we can have the relationship between the k and the omega. Okay, so if we look at here, okay, so you can see that we have the 2 pi over the lambda, right? It's just equal to the k and then times the v, and then equal to the 2 pi times the frequency, which is equal to the omega. Okay, so then finally we can conclude that the k here equal to the omega and then over the v. Okay, so this will be the wave vector, right, the relationship between the wave vector and the angular frequency. Okay, k equal to the omega and then over the v. Okay, okay, so now for the conclusions, then we can just write down equation of the y, right, to be, then we can get the wave function to be the y xt, right, is going to be equal to the a, and then times the psi, okay, of the kx, and then plus minus the omega times the t, and then plus the phi, and that's it. Okay, so this is going to be another form of the wave function of the sinusoidal wave. So from now on we can mainly use this one. Okay, we can mainly use this form, right, because this is equal to the k and this term just equal to the omega, so that's why we have the kx plus minus omega t and then plus the phi. Okay, so as promised, what is the difference between the plus and minus sign here, right? What is the difference between the plus and minus sign here? Okay, so let's say this: if we choose the plus sign, so it means that the wave will travel to the negative x direction. But then if we choose the minus sign, it means that the wave will travel to the positive x direction. Okay, so it means that the plus and minus sign here, right, it's going to tell the direction of the propagation of the wave. Okay, direction of the propagation of the wave here. For the plus sign means that the wave will travel to the negative x direction. For the negative sign, it just means that the wave just travel to the positive x direction. Okay, so if we look at this picture, right, you can see that the wave is traveling to the right hand side or to the positive x direction, then in this case we need to use the minus sign. Okay. One thing that you may notice from this picture, right, is that if we follow the motions of the particles on the wave, right, the particle will just oscillating up and down, just the same as the simple harmonic motions. Okay, so in this case, it means that the particles on the transverse wave will oscillate. The same as the simple harmonic motion, as we just mentioned already from the previous chapter, right? So in this case, it means that we can find the velocity and the acceleration of the particle moving in the simple harmonic motion here. Okay, so let's see this. Okay. Okay, so let's consider the velocity and the acceleration, okay, of the particles, right, okay, in the medium. Okay, so as we just mentioned before, right, so it's gonna follow, okay, so it's gonna behave as the simple harmonic motion, okay, or the SHM. So it means that we can find the velocity of the oscillation, right? We can find the velocity of the oscillation. Okay, so let's say that, okay, so now we just want to find the Vy. Okay, what does the Vy mean? The Vy here is going to be the velocity of the oscillation of the particle along the y-axis here, right? Okay, let's see. Okay, from the function, right, the y(xt), okay, equal to the a, and then times the sine of the kx minus omega t, and then plus the phi. So let me just pick the negative sign here. So let's say that the wave is just traveling to the positive axis. Okay, so let me just pick the negative sign. But now I just want to find the Vy, right? What is the Vy? The Vy just means that the dy and then over the dt. So it's going to be the derivative of the displacement y, right? Derivative to the times t equal to, okay? So let's make the derivative here. The a is constant, so we can just bring it out, okay? And then we need to take derivative of the sine function. Derivative of the sine function equal to what? Equal to the cosine of the kx minus omega t, and then plus the phi, right? And then we need to find the derivative of the arguments of the sine function. Right now we just take derivative of the t, okay? So it means that we just consider only this term. So it's just equal to negative of the omega, right? And then we're gonna have that equal to negative of the omega, and then times the a, and then times the cosine of the kx minus the omega t, and then finally plus the phi. That's the Vy. Now how about the acceleration along the y-axis, right? Just do the same thing. The ay equal to what? Equal to derivative of the Vy to the times t, right, equal to, okay. So now negative omega is constant, so we can just bring it out from the differentiation, right. Derivative of the cosine equal to what? Equal to negative sine, okay, just equal to negative sine. So it means that we have the negative the omega times the a, and then negative sine, right? So it's going to be the plus sign here, and then times the sine of the kx minus the omega t, and then plus the phi, and then find derivative of this argument, which is equal to the same thing, right, equal to the negative and then omega. So then finally we have negative the omega squared times the a, and then times the sine of the kx minus the omega t, and then plus the phi, right. But okay, let's see this. A sine kx minus omega t plus phi equal to what? It's just equal to the y, right? Just equal to the y. So in this case, we have that the ay equal to the negative omega square, and then times the y. So does it look familiar to you? Yes, right? What is this question? This question is the fundamental, right? The fundamental equations for the simple harmonic motions. Okay, so this one that we get. Oops, sorry, actually I should just say that. Okay, something like this. Okay, but one thing that I just want to show it to you. Okay, I just want to introduce you one equations. Okay, so it's called the wave equations. It's called the wave equation. So what does this mean? What is the wave equation? Let's consider this. Okay, instead of taking derivative of the t, right, but now I just want to take derivative of the x instead. Okay, of the x instead. Then I have that dv by dx, right, equal to, okay, so derivative of this one relative to the x, we have the a, and then times the cosine of the kx minus the omega t, and then plus the phi, right, and the argument of this one, which is equal to the k. Okay, so let me just put the k in the front. So we have the k times the a here. And now, okay, so let's find the another derivative of the dv by dx, right? So we get this one. Okay, so then it's just equal to the d by dx of what? The d by dx of this. Okay, we just take derivative of this one. Then again, right, let's see, equal to, okay, the k and then times the a, just constant, right, derivative of this one equal to the negative sine, okay, negative sine of the kx minus the omega t, and then plus the phi, and then find derivative of this argument, right, is going to be equal to the k square. Okay, equal to the k square. Okay, so now let's see this. Wait, actually, I forgot. So this one equal to the y. So let me just simplify first. And then times the y, okay? Because this term just equal to the y, right? So now let's see this. If I combine this equation and this equation together, okay? If I combine these two equations together, so for example, if I just sub the y here, right, into this equation, I'm gonna get that the d square y by dx square, right, it just equal to the negative of the k square. So now for the y, right, it just equal to the negative of the ay and then over the omega square, okay? But don't forget that the ay is equal to what? The ay is equal to the d square y by the dt square, right? So then here equal to, okay, we have the minus and minus sign combined together to be the plus, equal to the k square and then over the omega square, and then d square y by dt square, okay? So now this ratio, right, the k over the omega is just equal to 1 over v, okay, because the k equal to the omega over v, right? So it means that the k over the omega equal to the 1 over v. So in this case, we say that the k and then over the omega equal to the 1 over v. Then finally, if we plug in this into these terms, right, we're gonna have that the d square y by dx square is going to be equal to the 1 and then over the v square and d square y and then over the dt square, okay? So this equation, right, is called the wave equations for a sinusoidal wave. Sorry, A. Okay, the wave equation for the sinusoidal wave, it means that if we can derive that equations of the motions of any particle in any situation, right, has this form. So it means that that particle will move as the wave. So it's just quite similar to when we talk about the fundamental equation of the supersonic motion, right, from the previous chapter, that I say that if we have the particle moving and then if the equation of the motion has this form, so it means that the particle will move as the supersonic motion. So in this case, it's just the same thing, right? If the equations of the motion of the particle just look like this form, so it means that the particle will move as the sinusoidal wave. Okay, so now let's look at the examples.